So let's see what the key definition is. Now, the key definition itself may look a little bit sterile, but when we put it together with those couple of ideas that I just showed you, it comes out to be quite an important definition, and one that we're going to squeeze as much as we can in the future to get all kinds of other information. So the definition is the following. Let's say that we get a set of vectors v1, v2, vk. So just a set of regular vectors. By the way, notice that I'm not saying these have to be Euclidean vectors. We're going to see shortly some interesting things that happen in the context of linear independence for Euclidean vectors. But right now, this could be vectors in any vector space. So let's say we have a set of vectors like this. We're going to say that this set of vectors is dependent. And you might wonder, well, are we talking about independence or dependence? Well, the two are strictly related, as you can imagine, and it's easier to begin by telling you, first of all, what we mean by a dependent set. Well, this set is dependent if there's a set of scalars, C1, C2, Ck, same number of scalars as we had vectors, such that two things happen. Well, first of all, we want a linear combination of our set of vectors obtained by using these scalars to end up being 0, but such that these scalars are not all equal to 0. So the sum of their absolute values has to be greater than 0, which can only happen which can happen if and only if at least one of those coefficients is not 0. Okay, so let's see. So that means that a set of vectors is dependent if I can construct a linear combination by using not just the 0 scalars, but some scalars or a set of scalars, at least one of which is not 0, and that gives me the 0 vector. Otherwise, the vectors are called independent. Ooh, what does that otherwise mean? Well, let me put it another way. Another definition of independent, which is sort of independent of the first one, is as follows. We're going to say that this set of vectors is independent if whenever I consider a linear combination of them all and I end up with the 0 vector, well, this is only possible if all of the coefficients are 0. So in other words, the only way to combine the set of vectors through a linear combination and obtain the 0 vector is by multiplying each and every one of those vectors by the scalar 0. You want to think about this definition and what it means, and as soon as you're done with that, I'm going to give you a little bit of a more geometrical interpretation of what we're doing. Let's have a more practical, more visual look at this concept of linear independence and the related concept of dependence. We're going to do that by using geometric vectors. Now, first of all, when we're talking about dependent vectors, what we are talking about are vectors which are related to each other in some way. For instance, let's say that we have a plane, and in this plane, let's consider two vectors that go in different directions. So these two vectors are not related to each other in the sense that they're not multiples of each other. Well, in the case of only two vectors, that's the only way they can be related. And you can see geometrically that they are actually going in different ways. Now, if I think of another vector in the plane, it will be related to those two, right? So it will be some kind of a linear combination of the others. So it's not really pointing to anything new, to anything different. It's still using the same directions as the original two vectors. It's just going in the plane in a way which is already indicated, already dictated by the first two vectors. So this is really at the essence of being for a set of vectors to be dependent. There are some vectors in there which are not really saying anything new. They're repeating the same kind of information that the other ones have. In fact, as a little exercise for you, you may want to prove that in this case, when you have a set of dependent vectors, or which is equivalent, a dependent set of vectors, you may want to prove that in that case at least one of those vectors is a linear combination of the others. It's not always true that each one of them is a linear combination of the others, but certainly there are some vectors in there which are not saying anything new. They're just following along in what the other ones are saying. On the other hand, let's say that instead of this vector, we have an independent set of vectors. So they might be given by this third vector, which goes outside of the plane. So this gives an example of three vectors which will be independent. In what sense? In the sense that each one of them is giving something new, has a new, unique piece of information, unique piece of direction. So something which only belongs to it and does not come from the other ones. And again, following up on the previous exercise, you may also want to show that when you have an independent set of vectors or a set of independent vectors, you want to prove that none of them is actually a linear combination of the others in this situation. So each one of them is contributing something new.